Hi there everybody, and welcome to the next video of suspended classes. Assuming you watched the previous video, you have now understood that we will be spending time solving systems of differential equations. So section 7.1 is an introduction to actually solving these things. Last time we didn't solve any, right? I just set up the concept of a system of differential equations. In section 7.1, the goal is fairly simple. I'm just going to discuss a first method of solving 2x2 systems of differential equations. For the sake of simplicity, we're starting with two equations, two unknowns. Discussing this first method has two purposes. Purpose one is just to get comfortable with systems of differential equations as a concept. And secondly, start to understand what challenges can arise when you try to solve systems of DEs. This goal too will motivate subsequent sections. It sort of sets up why you would care about sections 7.2 and 7.3. Okay, let's first begin with a quick algebra review just to motivate what we will do with the systems of DEs. Here is a system of algebraic equations, something you saw in Algebra 2 or whatever over and over again. There are multiple ways to solve this system. Substitution is what people usually use. You could also use elimination if you wanted to. Some of you in high school may have used matrices to solve this. And matrices is actually where we're going, okay, with the differential equation material. If you don't know any of that, if you don't know about matrices, that's fine. But anyway, all I'm saying is there are multiple ways to solve this. Here's the substitution work. I don't need to tell you what's happening here, but you isolate a variable in one of the equations, substitute into the other, and learn what you want. This concept of substitution can actually be translated almost directly into solving systems of DEs. So let me show you how that works. Here is a system of differential equations. It's the same system from the previous video. How would you solve this by substitution? Well, how did substitution go? You picked one of the equations and isolated one of the variables. Okay, I'm going to pick this top equation here and isolate one of the variables. I'm going to isolate x2. I should say, just to save myself typing, notice I dropped the of t part. Okay, it's important to remember though, these are functions. x2 is a function, x1 is a function, both depending on time. So again, I dropped the of t just for saving myself typing, or if we were in class, I would do it to save myself writing at the board. But again, this is a differential equation here, so these are functions. Anyway, so x2 is x1 prime minus x1, right? Scoot that x1 over on the other side of this equation. Okay, well, once you've isolated a variable in one equation, you can then substitute it into the other equation. So let's just watch that go. To substitute this x2 into this equation, I need to put an x2 right here. I need to put a derivative of x2 right there. Okay, well, if x2 is this, x1 prime minus x1, then what's x2 prime? Well, it must just be, like you just slap primes everywhere, right? It must be x1 prime prime minus x1 prime. Okay, so what do you learn? If you substitute this formula for x2 into the second differential equation here, what you learn is that x1 double prime minus x1 prime, right? This is x2 prime. That must equal 4x1 plus x2, right? But what's x2? Well, we know it's x1 prime minus x1. So I just did a direct substitution. And then simplifying this a bit, so the 0 on the other side, I can scoot this 4x1 over, I can scoot that x1 prime over, this x1 over, and so on. If I just gather everything on the left, I end up with this. The second derivative of x1 minus twice first derivative of x1 minus 3x1 is 0. Okay, why is that useful? Why is it useful to have gone from this 2x2 guy, right, to this single differential equation? The reason this is useful is you know how to solve this. This guy I have highlighted. You guys can do that. That was a fair question on your first exam. It's a little confusing because I'm using a different symbol, but replace an x1 in your mind with a y. What if I asked you to solve y double prime minus twice y prime minus 3y? You guys know how to do that. It's just a characteristic equation setup. So let me just walk through that. Again, just imagine there's a y right here, a y right there, a y right there, equals 0, and so on. This is just a homogeneous constant coefficient dude from section 3.1 or whatever. So here's the solution. x1 of t, the roots of the characteristic equation are 3 and -1. So x1 of t is this. And boom, you have now learned what one of the functions was. Recall, though, that you must learn what both x1 and x2 are. Right? You need to know both variables that simultaneously solve both of the original DEs. But since we know that x2 is the derivative of x1 minus x1, what does that mean? That means if you know x1, you know x2. So here I just have written it. So here's the derivative of x1 right here, highlighted. And then there's minus x1. So when you simplify, you get this for x2. Twice c1 e to the 3t minus twice c2 e to the -t. So what does that mean? That means that anything that looks like constant e to the 3t plus other constant e to the -t combined with twice whatever this constant was here, this coefficient of the e to the 3t, you got to have double that here, minus twice whatever the c2 constant was. Okay, so the constants, you don't have complete freedom here, right? The c1 here matches the c1 here. Okay, so whatever appears here in x1, its double must appear there. So for example, what if c1 is 2 and c2 is 5? Then here's a concrete function, this x1. That x1 is part of a solution, and then as long as you double the c1 here, so you get a 4, and minus the double there to get a minus 10, you get a solution to the original system. Okay, so at this point, you should pause the video and see if you can mimic that exercise, that process with this system, and then here's the answer. Okay, so pause the video and see if you can do what I just did. All right, so assuming you are back after pausing, let's quickly finish up by talking about initial value problems. Here is the same system, but now notice I've put some initial values on the functions. I've restricted the functions with these two conditions. At time 0, x1 must be 3. At time 0, x2 must be 13. How do you handle that? How do you handle having initial values on your system? The answer is the same way you handled initial values in other contexts. You start by just ignoring them. So just like imagine covering them up. Just ignore that statement and ignore that statement and just solve the system here. Well, we've already solved it. Here's the solution. Right, that's from a previous slide. Okay, so once you have the general solution, the solution with the degrees of freedom baked in, right, these constants that can sort of roam, once you have that, then you remember, oh yeah, I had these conditions on my x1 and x2 functions now. So let's just unpack what those conditions mean. Well, x1 is this, right, this highlighted blue. So what is this initial condition saying? It's saying that in x1, when t is 0, x1 is 3. Okay, so 3, I plug in a 0 for t, and what do I get? A c1 plus c2. What is this condition saying? It's saying inside x2, when t is 0, x2 is 13. So I get this equation here. You plug in a 0 for t, and now you get twice c1 minus twice c2 equals 13. Okay, but what's this? This is now just a 2x2 system of algebraic equations, right? This is an algebra 2 problem now. So you can just ask Wolfram what c1 and c2 are, and there they are. Okay, so once you have that data, you know x1 is c1 e to the 3t plus c2, so on, right? You just plug those values in. So here's x1, and here's x2. Right, x2 has this coefficient of 2 there, and then that negative there. So this negative 7/4 becomes a positive 7/2. Okay, so anyway, if you can solve a system of DEs, having these initial values here doesn't conceptually change anything. You handle it the same way that you handled it back in chapter 3. Okay, so very quickly here, where are we going from here? Where are we going from section 7.1? 2x2 linear systems, like the example we just did, can be solved using substitution. It's a bit clunky, a bit tedious, whatever. It's nice in that it connects to Chapter 3, but it is a bit inelegant, perhaps. Beyond being inelegant, though, it does not generalize nicely to bigger systems. So imagine a 3x3 system like this. Imagine doing substitution on that. What would that look like? Well, in this first DE, you'd have to say isolate the x3, I guess, right? You get x3 equals like basically all these other three terms. Then you'd have to substitute that in here. But then you'd have two variables left over, both x1 and x2. So you have to isolate one of them and substitute down in here. And by the time you do that, you have a third order differential equation. So you can do it, but it's not it's not fun. It's tedious. It's also not particularly illuminating about sort of the qualitative behavior of this system. So you could always use substitution in principle, but for bigger systems, it's just like, it's ridiculous. The more equations you have, things just spiral out of control. So thinking back to just raw algebra, this system here, you may have been forced to solve in high school, perhaps using substitution. This, again, is not nice, using substitution. You could, again, isolate z in this first equation, substitute down into that z there, and then you have and into this z there, something, right? Then you have a 2x2 system, whatever. It's not ideal, right? So the question is, for either these algebraic systems or the differential equation systems, is there a better technique? And by better, I mean like not only just easier and faster, but a technique that maybe illuminates what these systems are doing, what the solutions are doing. Is there a better technique for solving algebraic linear equations that doesn't involve substitution? Right, this guy here. And the answer, again, some of you in high school saw this. If you didn't, it's fine. But the answer is yeah. Linear algebra is what you use to solve these things elegantly and quickly. Linear algebra, which is the theory of matrices, gives a general technique for solving linear algebraic systems like this. It turns out that linear algebra also is sort of the best way to solve systems of differential equations, although seeing where that linear algebra shows up is a bit more subtle than in this Algebra 2 problem. What does that mean for us? That means for the next two sections, actually, you'll be given a crash course in the linear algebra you need to analyze systems of differential equations. So that's where we're going. The next two sections involve no calculus at all. It, again, is just simply a crash course in the linear algebra we need to solve things like this. How would you solve this? Turns out you build a matrix, and the matrix tells you what you need to know. All right, well, that's it for section 7.1.